So now that we covered sources of acidity, we're going to get a little bit more into liming basics. So of course, liming being the management strategy that we employ to help counter acidic soil, to help neutralize some of that acidity in soils, okay? And we think about liming soils for a number of different reasons. The first foremost is to increase soil pH to make nutrients more available. That's really the fundamental reason that we lime soils. Liming is such a kind of universal phenomenon, and it's all about nutrient availability, of course, and that's why we're covering it to a large extent in this course. Other reasons include adding calcium and magnesium to soil. So some soils might have deficiency in calcium and magnesium, typically not those found in Ohio, but perhaps very acidic soils might have a lack of availability of these nutrients. We also think about reducing harmful concentrations of aluminum, manganese, and iron. These are acidic cations that can be problematic in terms of the actual physiology of plants, and so kind of ameliorating or reducing that, locking those sources up. And then finally, this fourth one, which really plays into kind of nutrient availability, but it's this idea of increasing microbial activity, increasing mineralization rates, and making nutrient cycling availability as optimized as possible. Let's think about actually how lime works, how lime reacts. A lot of people really haven't given much thought to this. Some might know that lime is this calcium carbonate, right? So it's calcium plus this CO3, this carbonate material. And we've got soil, with negatively charged soil with these positive cations. And so in the case of when it's an acidic soil, there's a lot of these hydrogen ions around, okay? So lime will react with this hydrogen. The calcium will replace the hydrogen on the exchange site. And then there's two, it will displace, because it's calcium plus 2, it displaces 2 hydrogen ions. It forms with that water, it makes water and carbon dioxide. So 2 H's plus calcium plus carbonate equals calcium, water, carbon dioxide on a mass balance. And so when we lime the soil, we essentially get water and carbon dioxide as a result, and a lot of that acid becomes neutral. So that's kind of the simple overview. Actually, there's really an intermediate step where we get this calcium that forms a H2CO3, that's carbonic acid, and then carbonic acid dissociates into water and carbon dioxide. Okay, so that's a little bit more chemically accurate in terms of what happens. And then, we also need to consider that calcium carbonate interacts with a lot of things besides just hydrogen. Aluminum also plays a large role. And so here we see this scenario of calcium replacing aluminum and hydrogen, and we're getting these byproducts of water, carbon dioxide, and then this aluminum oxides that occur. So, but really at the end of the day, we nearly always get water plus carbon dioxide as byproduct, and then we get some neutralized acid. Calcium replaces the acid on the exchange sites, depicted here as as a soil particle, and then calcium here. This is kind of a plate structure with aluminum. Aluminum gets knocked off, calcium takes its place, and then we've got aluminum oxide. Okay, so that's the process, kind of the chemical process of neutralizing that acid in the soil itself. So let's think about lime, and we're going to talk more about the concepts in this lecture and then go into some of the specifics in the next one. So lime applications are typically based on a 6 to 8 inch soil depth. Tilled systems in Ohio have been classified on somewhere between 0 to 6 to 0 to 8 inches. Continuous no-till systems, sometimes applications or recommendations, not on a state basis, but maybe an individual crop consultant might make these based on a 0 to 4 inch depth. So 4 inches can be sampled in kind of continuous no-till systems. Lime incorporation. After lime is spread, some kind of incorporation is often recommended. This is, of course, not in a true no-till system. This doesn't happen. It's like all things in a true no-till system. It's surface applied, and then it's left on the surface. But there's not a lot of acres that are like fully true no-till in Ohio. There's a lot of kind of minimal tillage or vertical tillage that happens where it might look at maybe the top 2 or 3 inches, but there's not a large inversion event that happens. So anyways, we recommend incorporating lime, and that's because lime that is not incorporated does not move through the profile very fast. Okay, so here's it can take 10 years or more for lime to reach 6 inches and raise the pH at that depth. Okay, so we just have a diagram showing. So lime was applied in 1985, and not incorporated or incorporated, and then they soil sampled 7 years later. Here we've got no lime. And the pH is, you can see this is a very acidic soil, about 4.5. Here we've got 6.5 tons that were, okay, let's look at this one, 6.5 tons that were not incorporated, so we can see that it raised its surface pH, and then it virtually had no effect at 3 inches, maybe a teeny bit of an effect. Down past 6 inches, no effect in terms of that. We've got 6.5 tons that was applied and then incorporated, and so we can see the pH at the surface being the highest, but then really dropping, still affected at 6-inch depth and blah, blah, blah. And then when we increase that rate from 6.5 to 9.5, we can see that it has a lasting effect. Okay, so the point is just a little schematic to show, it's based on real data, but it shows that when you do not incorporate lime, it does not move. You really just neutralize that surface area. And so when you talk to continuous no-tillers, people that are kind of die-hard no-tillers, they will tell you that they use a lot of lime, and it's to neutralize that surface layer, and then they try to really drive that surface layer to almost pH neutral, and so some of these sublayers will kind of become more and more neutralized over time. So it's a long-term process. Continuous no-till system soil stratification happens quickly. This is just going on to what I was alluding to. Large portions of cations removed from soil surface, okay? And then when we think about and fertilizer applied, there's a lot that happens right at that kind of surface. And so pH can drop quickly. And we often think of no-till systems where it's common for no-tillers to apply lime more frequently, maybe every 2 years or every 3 years, and not just every 3 or 4 years. And liming frequency, will depend to a large degree on the soil type, the removal rate, the rate of acidification, et cetera, et cetera. And so again, we can look at these kind of two-tilled systems. We have 2 different nitrogen rates of 150 pounds versus 300 pounds, very high rates here. We've got an unlimed soil that's conventionally tilled, okay, and so here are pHs of 5.2 at 0 to 2 inches, 5.6 at 2 to 12, and then 5.7 at 6 to 12 inches, okay? So our unlimed with the low rate and our unlimed with the high rate, and you can see already that the high rate and fertilizer acidify soil to a larger degree than the lower rate. And then we can look, so this is conventionally tilled. These values aren't particularly that different from each other, 5.7 to 5.2. But in an unlimed no-till system, so the difference between these two boxes is conventional till versus no-till. We can see a large difference, 4.8 down to 5.9. So that's a whole, 1 unit. So essentially that surface 0 to 2 has 10 times the acidity, roughly 10 times the acidity is at 6 to 12 inch. And then when we add more fertilizer, more acid, essentially, more nitrogen. Fertilizer, which is an acidification source, it takes it from 4.3 to 5.5. So that's over, again, this is 10 times more acidic, more than 10 times acidic in the surface than it is in the sublayer. So, and that's the result of a system that has not been, that those layers have not been tilled, have not been incorporated and mixed. And it's really at that surface 2 inches where there's a lot of cations getting removed, the fertilizer is applied, the microbial decomposition occurs, root activity is concentrated at that surface. Again, all these things we talked about in the last lecture about sources of acidity are acting to a larger degree in that 0 to 2 surface layer than in the 6 to 12 layer. So again, tillage is an important tool to combat kind of acidification in terms of mixing layers, and incorporating that lime to neutralize that acid. So lime application, we typically would recommend it every 3 or 4 years. Soil testing is critically important. We'll talk a lot more about soil testing as the semester goes on, but really it's a fundamental piece of managing soil fertility. And if you're not soil testing, you're just really left in the dark in terms of what you need to apply and at what rates and how often. Without soil testing, it's really unlikely that you're running a profitable business in terms of farming if you're not soil testing for that. So, and soil testing for pH alone is sufficient, in my mind, sufficient justification to soil test, right? Like if that's all you're going to do, soil test and test pH, it's worth doing it. So, every 3 or 4 years would be typical. Sandy soils, i.e. soils that are less buffered, more frequent applications are better. For clay soils, larger applications, less often is fine. So, even a 5 or 6 year time frame, depending on the soils and how, the rate of change, et cetera, would be fine. But a lot of people, their cycle might be every 3 or 4 years they do a lime application. It's common in the fall to apply lime in Ohio. It gives time for that lime to react. Lime doesn't react instantaneously, and so it takes some time for that reaction to fully run its course and to lower and gives time to react. And it says at lower pH. It should say raise pH here. It reduces compaction and avoids planting delays. So fall is often a time when our soils in Ohio are dry. Soil sampling often occurs in the fall because it's easier to get out to take soil samples. It's easier to apply product in the fall, and we're not worried about delaying our planting window, which is a critical piece for profitability in Ohio. So hay and pasture, obviously there's no incorporation in a long-term hay or pasture system because you've got perennial vegetation there. So we really want to fix or address any issues that we have in pasture or hay fields before we seed, and do that several months in advance if possible. We can always think about kind of surface unincorporated applications, but again, not as effective as if it gets fully incorporated. One little caveat about interactions with lime and nitrogen. Okay, so we don't recommend applying a urea or ammonium-based fertilizer soon before or after applying lime. And that's because there's a chemical reaction that happens with lime and ammonium, and it's a pH-driven phenomenon. So a couple reasons, right? So here we say there's a graph showing percent seed germination with volatilized ammonia. And so as your volatilized ammonium, we'll talk about this NH3 being lost as a gas when we get into the nitrogen cycle. As that increases, we can see our percent germination really decreases. So there's, this is really harmful for seedlings. But we can see that as a kind of excuse me, as a pH a kind of base phenomenon, this idea of ammonia versus ammonium. So ammonia is NH3, ammonium is NH4, and as pH increases, the percentage of ammonium that turns to ammonia and gets volatilized increases. So we don't like to apply lime with nitrogen fertilizer. Now, one of the differences, or one of the things that makes this a little different, or kind of a caveat, I suppose, is that we just talked about, fall applications are really important, and that's when most of the lime is applied. Certainly not all the lime. There's plenty of lime that's applied in the spring, but we typically like to do it in the fall if possible. And sometimes we'll apply some ammonia-containing fertilizers in the fall with like phosphorus. So monoammonium phosphate MAP or diammonium phosphate DAP might also get applied with that lime. And it's true, it will increase that risk of nitrogen loss, but oftentimes when we're applying DAP or MAP as a phosphorus form, we're applying it for phosphorus in the fall for the following year and not really thinking about the nitrogen that's applied with that. So we're not really counting on that nitrogen being there. So anyway, so this is just something to keep in mind when we're thinking about lime application. We don't often want to apply common sources of nitrogen fertilizer with it. So there's a number of factors that influence frequency of liming. So soil texture being a large one. Soil texture is going to drive that CEC and the ability of that soil to resist changes, and pH change being one of those. Rate and type of end fertilizer has it's a large acidification event and a large source of acidity. So how, depending if you're growing a really nitrogen-loving crop, something like corn, versus something that requires very little nitrogen, is going to influence the amount and level of acidification that occurs. In the same sense, the rate of crop removal of calcium, magnesium, but also other cations is an important factor in that. The amount of lime that you apply, of course, is going to influence this. If you just do a small amount, and you might want to do that on a yearly basis, or if you do a large slug, and that might happen, every several years, for example. The pH range desired and the tillage system. So these are things that we've already talked about. If your pH is really, really low, you come into and start farming a new field or a new system, and you got pHs that are really out of whack, you're going to want to apply more frequently to kind of get that ship righted, rather than if you come in and you're like, oh, what's a pH of 6, and I just want to bump it up a teeny bit. So these are all things that we need to kind of consider when we think about how often we're actually gonna lime. Okay, so subsoil acidity. When we think about subsoil, this would typically be below the tillage depth, typical tillage depth of 6 to 8 inches. And so, we have, especially in eastern Ohio, really acidic subsoils. And so we might think about, trying to neutralize that, because we know that crop roots typically grow, much deeper than 8 inches. And so thinking about neutralizing some of the acidity in those lower layers, but we don't have really the ability to incorporate or mix that lime in there. But this is just showing a couple different slides to show that it takes time, but applying at 2 tons per hectare of ag lime per year, and I can't recall how frequently this was done, but you can see the limed in blue and the unlimed in red, and then pH, soil pH on the vertical axis over depth. And you can see this kind of trickle-down effect that happens when we lime. It's really the surface layers that are most affected, but over time, that pH, that lime does have an effect on soil pH, albeit not very large, but it goes through the surface profile. Okay, down to 40 centimeters. That's whatever this is, 38 centimeters. It's almost a 1.5 feet or so. So it's that does happen. And here we can see the effect of surface soil pH on subsoil pH. And so again, pH at various steps with increasing soil pH. So here we've got a pH of 4.9 all the way to 6.5, and then that liming event, like no liming versus liming, and then how that influences at 14 to 22 inches. Okay, so that's well over a foot, and we can see that lime soil, and as this the gradation at the surface from 4.9 to 6.5, that kind of carries through. So at these lower depths that have not been incorporated. So again, there's an element of time that's taken place. If you would go out and you'd had a soil at 4.9, and then you'd apply different lime rates, and then change in the first 6 months, it would go from 4.9 to 6.5 or across this gradient. We likely would not see in the lower profiles this difference, right? They might all be 4.7 in the lower profile. But with given enough time, that acidity will get neutralized and that lime will work its way down the profile. So it's not to say that it doesn't happen or that lime, once you apply it, doesn't move. It's just that it takes time for that to happen. Okay, so pH effects on nutrient availability and yields. It's, I guess, taken for granted that pH increases yields. That's it's one of the first things that you can do when you're growing crops to increase availability. Here's just some evidence that shows this, again, these kind of tables from our Haviland textbook. Different lime rates, okay, from 0 to 8 tons per hectare are pHs that are affected by that lime rate, and we can see that we overshot here. We took it, depending on what we're growing for most field crops, we wouldn't want it to get above 6.8, but at an 8-ton application, we took it above neutral into alkalinity, so that's not really what we'd like to see. But what does that do for our available phosphorus rate? So this is an extraction that is not a total, but it's actually like an available extraction of P and K. And we can see it goes from 19 and then starts as that pH increases. Now there's some wiggle room, and it's not a perfect fit here, but we can see as that soil pH increases above say 6, that's when our available phosphorus really starts taking off in terms of availability, and that number starts increasing. Calcium the same degree, etc., etc. And what happens when we do that? So, I'll mention that potassium to a lesser degree becomes more available, but as we increase pH, increasing cation availability that happens. Okay, magnesium, the availability increase. You can see general trends in this table. And it's, we don't live in a perfect world, right? So there is variability, but calcium, magnesium, phosphorus, these things increase as your pH increases. And then thinking about, again, liming rate versus wheat yield, we increase, as liming rates increase, our soil pHs increase, and then our wheat yields increase. Our aluminum concentrations essentially get driven to 0, okay? So at a pH of 4.6, 102 part per million aluminum is essentially causing some aluminum toxicity, and that's driving our wheat yields down. And then again, this generalized relationship that we see about effective increasing pH on wheat yield. So here we can see at pHs below 5.3, our wheat yields really decline. When we get above 5.3, the effective pH on wheat yields is pretty minimal, and it essentially plateaus. So, just a little bit of data to show what most people assume, that liming soil increases not only the nutrient availability, but increases crop yield for the most part. When we don't have a lime situation and we think about plant growth problems in acidic soil. So what are some of the mechanisms? Again, we won't touch, we're just really going to touch on this a little bit. We're not going to get into the nitty-gritty physiology that you might in a plant phys class, but common toxicity problems associated with low pH are aluminum, manganese, and hydrogen toxicity. It's really aluminum and manganese at low pHs. We don't really particularly think about hydrogen toxicity, but that might occur, say, in the plant itself. So here we got root length versus pH, and we can see as pH increases, our taproot and our lateral roots all increase. And the reason, not the mechanism, but this is a symptom of the fact that as roots are trying to grow in very acidic soils, we see toxicity essentially at that root tip from aluminum and manganese. Okay, so at low pHs, the solubility of these cations increases and become toxic to plants, and then at higher pHs, i.e. when we lime and neutralize them, they become less and less available, and so aluminum toxicity, manganese toxicity become much less of an issue, basically driven to zero. And you really have to get really low pH. pH is below, say, typically 4 or 5 for a lot of aluminum. For aluminum toxicity really to be a problem. And so on the flip side of toxicity, we can think about deficiency of nutrients that we actually do need: calcium, magnesium, and phosphorus. And these are cations that are, strongly driven by pH effects. We talked about base cations and base cation saturation as a function of pH. Okay, and so when pH is low, calcium, magnesium by default are going to be relatively low, and phosphorus is a nutrient that is very pH dependent, and so in highly weathered acidic soils that we might find in the southeast or in tropical environments, P is the most commonly limited nutrient for growth. Okay, so and then it's not just aluminum, manganese toxicity. It's not just calcium deficiency, etc. There's a number of different reasons. There are a number of different mechanisms that we could cite why low pH soils can be bad for plants. So lots of reasons. Here's just a table that talks about some of these things. Say aluminum manganese toxicity occurs at pHs less than 5 to 5.5, and when we lime, exchangeable aluminum in the solution is going to decrease. Okay, as pH increases. Hydrogen toxicity occurs less than 4, so again, we've got to be quite a bit lower. A full 10 or 10.5 times or 15 times, less than what the mechanisms for aluminum and manganese. But you can look at some of these other ones. Just kind of skim through this table. Nitrogen deficiency, for example, occurs when pHs are less than 5, and this is because a decreased nitrification, mineralization, low organic matter. Again, these are effects that we see on the microbial community per se that have ramifications for the overall availability of nitrogen, phosphorus, potassium, etc. So plant growth problems in acidic soils, there's a number of reasons that this happens. Kind of generally we see the plant as having a really hard time struggling, but mechanistically this table kind of elucidates some of these mechanisms that occur for each individual nutrient. Okay, so we'll stop there. We'll pick up next lecture talking a little bit more about lime recommendations.